All right, so supposing that we're going to compare chemistry to baking for a moment, and there's not a lot of difference here. In fact, a lot of chemical reactions do happen when you're baking things. So you look at our chocolate chip cookie recipe here. Um, Suppose that you only had 1 cup of flour, but you had enough of all the other ingredients. What would you need to do?
I really don't know.
Half everything else.
Okay, half everything else. Because if you try and make the recipe with just 1 cup of flour, it probably won't turn out right. Well,
Man, when it
With-
says large egg, is it talking like an ostrich egg or a large chicken?
you know, when you buy eggs at a grocery store, they have different sizes, and you might be able to substitute a medium egg instead of a large egg or something. I don't know. All right, now let's just suppose that we were. Let's suppose we were trying to do this reaction with the nitrogen and the hydrogen, and let's say that we had 1 mole of nitrogen and we only had 1 mole of hydrogen. Would we be able to make 2 moles of ammonia? No. How much ammonia would we be able to make if we only have 1 mole of hydrogen?
Would you be able to make any? If you don't, if you have
Like 0.8.
2 and it's 1 mole, and that means you need 1.5 moles of hydrogen. But if you only have 1 mole of hydrogen, then I don't think you can make any nitrogen.
Well, you could make. So if we have 1 mole of nitrogen, 1 mole of hydrogen,
Oh, you make less than
we would run out of hydrogen first, right? We'd use all of that up. And we would be able to make 2/3 of a mole. Basically, it's going to divide our total by 3. We'd be able to make 2/3 of a mole of ammonia. How much of the nitrogen would be left over? Okay, the ratio they go together is 1-3, right?
Yep.
Okay, so if we had 1 mole of this, we would only need how much? Yeah, we'd only need 1/3 of a mole of nitrogen, so we'd have 2/3 of a mole of nitrogen left over after the reaction happened. And I think I get what you were saying earlier about would it be able to go. Well, I'm saying moles, not molecules. If we're saying molecules and we only had 1 mole of hydrogen, no, it wouldn't be able to go. If we only have 1 molecule of hydrogen, yeah, you wouldn't be able to make any ammonia. So, all right. So let's take a look at this limiting reactant problem. So the limiting reactant is the reactant that is present in the smallest stoichiometric amount. And what that means is that it's going to be the reactant that is used up completely by the reaction. The other reactant that is present is the excess reactant, and it is not used up completely by the reaction. The way that you know that you have stumbled upon a limiting reactant problem versus the other problems we did, like the ones yesterday, how many substances were we given the amount of in the problems we did yesterday? We're given the amount of one substance in all of these problems. Now, with I'm putting these up here so if somebody's watching them, they can get them since they didn't get them yesterday.
Yeah.
Okay. Thanks to the camera freezing up. But anyways. All right. So this one, how many reactants are we given the amounts of this time? 2. And this is really hard for chemistry students based on previous experience of mine that for whatever reason, you'll read this and it just doesn't register, hey, they're giving me the amount of both reactants. You have to have that thought of like, well, I wonder which one of them I'm going to run out of first. So unlike the recipe, which is easy for us to kind of think through, this is much more difficult because they gave us grams, but really when reactions happen, they don't happen on a basis of a ratio of grams. They happen on a basis of a ratio of moles. So we will have to convert our grams to moles before we'll be able to do any kind of comparison. And there's a couple of different ways to find the limiting reactant, but I'm going to show you the method I think is the most straightforward, and then we'll work through that. So let's start off and just set up the structure of the problem here. So the unknown, we want to know how many grams of water are produced. But before we can find the grams of water produced, we need to find the limiting reactant. What would be a really nice abbreviation for limiting reactant? LR. So we're also going to find the limiter, and really this is going to come first, and then we'll figure out how many grams of water we made out. So I guess I should switch the order of these. And you don't have to write this every time, but just if you want to make yourself a note, how do I know I need to find the limiting reactant? Well, when you're given two reactants, that's how you know. So make sure when you're solving these problems, you think about it, because they don't always say find the limiting reactant. All right, the knowns, we're given two of them, 2.70 grams of butane or C4H10 and 6.3 grams of oxygen. All right, and here's to having a plan. Okay, like the other stoichiometry problems, what do we probably need to do before anything else? We're going to write the reaction. And then we're going to find the limiting reactant. And then find water, because that's what they asked us to do. Now, I'm simplifying the plan because I don't want to make you write a ton of stuff over here. But yeah, we're going to have to do all the grams to moles to grams like we did in the previous stoichiometry problems. But I'm not going to make you write out a tremendous amount of stuff here because it'll probably confuse you more than anything else. All right. What type of reaction is this? C4H10 and oxygen. Yeah, it is combustion. So the products of combustion are always what? Yes. Carbon dioxide and water. Balancing these can get interesting. This one, I'm looking at the hydrogen first. Okay, 10 hydrogens here. Help if I put the O on the water. So if I wanted to get 10 hydrogens over on the right side, I would put a 5. That would give me an odd number of oxygens, because 5 times 1 oxygen gives me 5, and then whatever is here is an even number. I can't get an odd number of O2 on this side. So what should I do to fix that? Double it. I'm going to throw a 2 in front of that. That'll make this be a 10. The carbon there's 8 of them. And then, 13? Yeah. All right. So now it's balanced. All right. So we've written the reaction. Now we need to figure out what the limiting reactant is. The way that I've found, I think, makes the most sense to me is to use one of the products and solve for the other one. So let's give that a try and see how it turns out. And it doesn't matter. We can either take the 2.70 grams of C4H10. I think I said price, one of the reactants, and solve for how much of the other one we need. So we can either take the butane that we're given and solve for oxygen, or take oxygen and solve for butane. Does anybody have a preference which one we do? We'll get the same answer either way. You want to do what? You want to solve for oxygen? Let's do it. So if we have 2.70 grams of butane, and we want to know how much oxygen we need to go with that. Let's do that and figure out if it's more or less than 6.30 grams. Let's see, molar mass of butane, 12. Wow, that one is dead. Let's try again. All right, 12 times 4 plus 10. All right, 58. All right, now I'm going to use the mole to mole ratio to go from moles of butane to moles of oxygen. The reaction says that 2 moles of butane go with 13 moles of oxygen. So moles of butane cancel out. And then one more step will get me from moles of oxygen to grams of oxygen. And now, let's see, 32. All right, so moles of oxygen cancel out. And then we'll plug that into the calculator. So 2.70 times 13 times 32. And then divide it by 58 times 2. Put the 58 times 2 in parentheses. I got 9.68.
Let's say compare.
Yep, compare. Now, the hardest thing that you're going to do here is figure out which one, or like what this means, basically. It's going to be the hardest thing. We calculated that we needed 9.68 grams of oxygen to go with the 2.70 grams of butane. But we only are provided 6.30. What does that mean?
That means you
They can't have it.
You don't have enough.
is going to run out first.
The oxygen is going to run out first. So what does that mean? What is oxygen? Limiting or excess? Limiting. And what is the butane, since it's not going to run out? It's the excess. Okay. So what you can do now is somewhere we can label. I'll do it here, or I'll just write it down here. That's fine. Okay. Now that we know that, what we can do is we can calculate and find how much water. So we found the limiting reactant. We're going to find the water. Let me specify here using the limiting reactant. So if we know this is going to run out, then this is going to set the amount of water that we can actually make, rather than the 2.70, because we know we're not going to use all the 2.70, but we will use all of the 6.30 grams of oxygen. So let's set up our stoichiometry to do that. 6.30. All right, the chemical reaction will take us, keep an eye on my time here, about to run out. All right, so we worked this out, and we got 2.73 grams of water. If we used the excess reactant, we would have gotten a larger value, and that would not have been correct because we're not going to react all of the excess reactant.